Okay, so now we're going to switch topics a little bit and finally enter the last main theorem for this class, which is the Divergence Theorem, and this one is related to flux. So flux is the other key concept on vector calculus, which is sort of opposite in a way to the line integrals we have been doing for computing work. And so what do I mean by that? Let's recall how we were thinking about work. Imagine that you had a curve, which for now I'll think of it as a closed curve. So you have a closed curve here. And work, if you have a vector field f, right? Let's say this is your vector field. The work along this curve, right, was the integral of the force field, or this vector field, with the velocity vector of the curve dt, say from some time, initial time, to some final time. Now, how can you think about this dot product? Well, here you have the velocity vector is tangent to the curve. So here you have the velocity vector. Here's another velocity vector. Here's another velocity vector. And so you see, when you do a dot product, right? This is the angle between the velocity and the force. And the dot product, if you remember the beginning of this course where we talked about projecting one vector along the other, this dot product has to do with the component of f, which is tangent to the curve, because it has to do with a component of f which is parallel to b, to the velocity. So component of f tangent to the curve. Okay. And so when we compute work, we actually only care about this tangent component, because this is the thing that you're integrating. So what you can think of is what happens with the other component, right? So what I'm trying to say is that the force decomposes into two pieces, one which is perpendicular to the velocity vector, one which is parallel to the velocity vector. Okay, let's call this f perpendicular and f parallel. Again, this should seem familiar from the discussion about projecting a vector along another one. And so the parallel component is the one that we are using here, or the magnitude of the parallel component. Well, it could be negative. So this is related to the parallel component. That's what I'm trying to say. So the parallel component is related to the work. And so the question is, what about the perpendicular component? And so in order to think about this better, let's draw this again. And let's reinterpret a little bit what this force is supposed to be. So here we have our curve. Imagine that on the xy plane you have a fluid, and you have a particle on this fluid, and f now represents the velocity the particle has at that point, or the fluid has at that point. So at each point you draw a vector which now represents the velocity of the fluid at that particular point. And so you want to ask whether or not through this region, maybe there's a net gain or loss of fluid. Maybe there's more. Well, you can imagine also that there's fluid outside this region, so some of the particles could be entering through this membrane, this pink curve. Some will be exiting through it, right? And so you want to understand whether or not the region is gaining or losing mass in a way. And so let's follow one of these particles as you move closer and closer to the boundary, because the mass can only escape through the boundary or can only enter through the boundary. So the critical place to study for understanding if there's net loss or gain of some material or of some substance is what's going on at the curve. And so let's say you choose a particle precisely at the curve, so it's about to exit the region, and here it has a velocity in this direction. Now, which is the component of the velocity responsible for making this particle exit the region? Well, if you think again about decomposing the velocity into two pieces, right? The perpendicular and the parallel one. The parallel one will not force the particle to exit. It will just make the particle move along this curve, which is okay. I mean, you're just in the limiting situation. So the parallel component of the velocity is not important in this case. The component of the velocity that would be ultimately responsible for you leaving this region will be the perpendicular component. So what I'm trying to say is that the net gain or loss of fluid that's related to the perpendicular component of the vector field. So in a sense, if you're exiting, like if the velocity happens to be completely parallel, if at a point the velocity happens to be completely parallel to the curve, there's no loss here, and the extreme opposite is where when the velocity happens to be completely perpendicular to the curve, in which case exiting this region is as easy as possible. You're not losing like energy or speed being spent in moving along the curve. So you see, this is why I was saying that this concept is opposite to the one that we were using for curves for computing work, because work only cares about the tangential component, and now from this perspective, what we care about is about the perpendicular component. And so more generally, what we could have is a surface. Let me show it again with my net. So now you could have a surface. It doesn't have to be closed. You just have like some membrane in space. Imagine I place this on a river, right? And so you can ask what's going on with the particles of fluid through this surface. And again, whether or not there's a net gain or loss of fluid has to do with the velocity vector of the particles as they move through the green surface. And so the velocity vector, the surface will have some normal vector, right? Every surface has a normal vector, and if this is the velocity vector of one of the particles, then the only thing that matters to determine if the particle manages to escape through this surface is what happens with the component of the velocity which is parallel to the normal vector. In other words, what I'm trying to say is that you could have, and this is a concept of flux, so you could have some surface as you have some liquid, some fluid going through the surface, and the surface has so this fluid, this F now represents the velocity of the fluid, and so N is a normal vector to the surface, and what I'm saying is that the component of the velocity vector, which is entirely responsible for making the fluid exit through this surface, is related to the component of the vector, which is aligned with the normal vector. And so that has to do, again, this is like a projection of this vector along this vector, and so that has to do again with the dot product. And so we say that the flux through a surface. So my recording system keeps crashing, but what I was just saying is that you only care about the component of F parallel to the normal vector, and so the definition of flux through a surface S, which is usually denoted V sub S, is just going to be the integral of this component, this normal component of the velocity vector, over the entire surface. So these are similar to the surface integrals that we did before. Is now that instead of putting like the dot product between the curl and N, now we're just taking the dot product between F and N. And so, as I'm saying, N is a unit normal vector to the surface. And what we will do in the next example, in the next video, is do an example where we compute the flux. The point is that this is like the official definition of flux, in the same way in which the official definition of the work was in terms of a line integral. But then with Stokes' theorem, you realize that you could compute the work using the curl of the vector field and a different integral. And what will happen here is that in the same way, instead of using the official definition of flux, you can compute the flux using the divergence of a vector field, which I still haven't told you what that is. And you have to integrate the divergence, do a different integral which involves the divergence of the field. And so that's where we're trying to get at, and that will be the last topic of this class. So here's an animation of how you should think about flux. Remember, the idea of flux is that it represents the amount of material or substance that goes through a specific surface. So in this case, you have our surface is this square, and we have maybe a cross section of some tube where water is running through, and so we have this fluid represented by these vectors. And the idea is that well, in this case, all the fluid must pass through the surface as it moves along the tube, and so in this situation the flux is maximal because the velocity and the normal vector to the surface are completely aligned. So in other words, the angle is 0, so cosine of 0 is 1. And so here you can see an animation of all the particles having to go through this surface. But now the idea is that as you vary the angle, say now an angle of 25.2 degrees, then the flux is smaller, because some of the it's harder for the particles to pass through the membrane. And so you see here that there's smaller flux per unit time. I mean, flux is per unit time, so what I really mean to say is that it takes longer for the particles to go through this surface. But let me stop it again. And in the maximal case, where the angle is 90 degrees, then there's really no contribution between none of the particles go through the surface. They're just tangent to the surface. So which is what you see here, that the flux is 0. So if there's an angle, the point is that if there's an angle between the velocity vector and the normal vector of the surface, between the velocity vector of the particles and the normal vector of the surface,
Then there's like the velocity decomposes into component perpendicular to the surface and tangential to the surface, and the part that's tangential to the surface is sort of is not contributing to escaping the surface, and so that's why only the normal component matters for the flux.